Lesson objectives: define atomic number, define mass number, understand how isotopes differ from one another, and be able to designate them by various methods. Be able to calculate the average atomic mass of an element. Lesson vocabulary: atomic mass unit, atomic number, isotope, mass number, nuclide. Check your understanding. Recalling prior knowledge. How does the number of protons in an atom compare to the number of electrons? What is the charge and mass of the neutron? Introduction. Atoms are the fundamental building blocks of all matter and are composed of protons, neutrons, and electrons. Because atoms are electrically neutral, the number of positively charged protons must be equal to the number of negatively charged electrons. One of Dalton's points in his atomic theory was that all atoms of a given element are identical. In this section, we will see how this is not strictly true, thanks to variability in the number of neutrons that an atom may contain. Atomic number. The atomic number, Z, of an element is the number of protons in the nucleus of each atom of that element. An atom can be classified as a particular element based solely on its atomic number. For example, any atom with an atomic number of 8, its nucleus contains 8 protons, is an oxygen atom, and any atom with a different number of protons would be a different element. The periodic table, figure below, displays all of the known elements and is arranged in order of increasing atomic number. In this table, an element's atomic number is indicated above the elemental symbol. Hydrogen, at the upper left of the table, has an atomic number of 1. Every hydrogen atom has 1 proton in its nucleus. Next on the table is helium, whose atoms have 2 protons in the nucleus. Lithium atoms have 3 protons. Beryllium atoms have 4, and so on. Since atoms are neutral, the number of electrons in an atom is equal to the number of protons. Hydrogen atoms all have 1 electron, occupying the space outside of the nucleus. Lesson content. Figure 1. The periodic table of the elements. Mass number. Rutherford's experiment showed that the vast majority of the mass of an atom is concentrated in its nucleus, which is composed of protons and neutrons. The mass number is defined as the total number of protons and neutrons in an atom. Consider the table below, which shows data from the first 6 elements of the periodic table. Atoms of the first 6 elements. Name symbol atomic number protons, neutrons, electrons, mass number. Hydrogen H11011. Helium He22224. Lithium Li33437. Beryllium B44549. Boron B556511. Carbon C66612. Consider the element helium. Its atomic number is 2, so it has 2 protons in its nucleus. Its nucleus also contains 2 neutrons. Since 2 plus 2 equals 4, we know that the mass number of the helium atom is 4. Finally, the helium atom also contains 2 electrons, since the number of electrons must equal the number of protons. This example may lead you to believe that atoms have the same number of protons and neutrons, but a further examination of the table above will show that this is not the case. Lithium, for example, has 3 protons and 4 neutrons, giving it a mass number of 7. Knowing the mass number and the atomic number of an atom allows you to determine the number of neutrons present in that atom by subtraction. Number of neutrons equals sign mass number, atomic number. Atoms of the element chromium, Cr, have an atomic number of 24 and a mass number of 52. How many neutrons are in the nucleus of a chromium atom? To determine this, you would subtract as shown. 52 minus 24 equals 28 neutrons in a chromium atom. The composition of any atom can be illustrated with a shorthand notation using the atomic number and the mass number. Both are written before the chemical symbol, with the mass number written as a superscript and the atomic number written as a subscript. The chromium atom discussed above would be written as 52, 24, Cr. Another way to refer to a specific atom is to write the mass number of the atom after the name, separated by a hyphen. The above atom would be written as chromium-52. Isotopes. As stated earlier, not all atoms of a given element are identical. Specifically, the number of neutrons in the nucleus can vary for many elements. As an example, naturally occurring carbon exists in 3 forms, which are illustrated below, figure below. Lesson content. Figure 2. Nuclei of the 3 isotopes of carbon. Almost 99% of naturally occurring carbon is carbon-12, whose nucleus consists of 6 protons and 6 neutrons. Carbon-13 and carbon-14 with 7 or 8 neutrons, respectively, have a much lower natural abundance. Each carbon atom has the same number of protons, 6, which is equal to its atomic number. Each carbon atom also contains 6 electrons, allowing the atom to remain electrically neutral. However, the number of neutrons varies from 6 to 8. Isotopes are atoms that have the same atomic number but different mass numbers due to a change in the number of neutrons. The 3 isotopes of carbon can be referred to as carbon-12, 12, 6C, carbon-13, 13, 6C, and carbon-14, 14, 6C. Naturally occurring samples of most elements are mixtures of isotopes. Carbon has only 3 natural isotopes, but some heavier elements have many more. Tin has 10 stable isotopes, which is the most of any element. The term nuclide refers to the nucleus of a given isotope of an element. The nucleus of a given carbon atom will be one of the 3 possible nuclides discussed above. While the presence of isotopes affects the mass of an atom, it does not affect its chemical reactivity. Chemical behavior is governed by the number of electrons and the number of protons. Carbon-13 behaves chemically in exactly the same way as the more plentiful carbon-12. Sample problem 4.2. Composition of an atom. How many protons, neutrons, and electrons are present in each of the nuclides below? Iron Fe. Atomic number equals sign 26, mass number equals sign 56. Iodine 127. Atomic number equals sign 53. 31. 15. Step 1. List the known and unknown quantities and plan the problem. Known, atomic number and mass number for each. Unknown, number of protons, electrons, and neutrons. Each shows a different way to specify an isotope of an atom. Use the definitions of atomic number and mass number to calculate the numbers of protons, neutrons, and electrons. Step 2. Calculate. Number of protons equals sign atomic number. 26, 53, 15. Number of electrons equals sign number of protons. 26, 53, 15. Number of neutrons equals sign mass number atomic number. 56 minus 26 equals 30. 127 minus 53 equals 74. 31 minus 15 equals 16. Step 3. Think about your result. For each atom, the results are consistent with the definitions of atomic number and mass number. Do the practice problems below. If necessary, refer to the periodic table, figure above, for the atomic number or symbol of the given element. Practice problems. How many protons, neutrons, and electrons are there in the atom? 19.9f. How many protons, neutrons, and electrons are there in an atom of lead-207? A certain atom has an atomic number of 36 and a mass number of 84. Write out the designation for this isotope in both nuclide symbol form and in hyphenated form. An atom has a mass number of 59 and contains 32 neutrons in its nucleus. What element is it? Atomic mass. The masses of individual atoms are very, very small. However, using a modern device called a mass spectrometer, it is possible to measure such minuscule masses. An atom of oxygen-16, for example, has a mass of 2.66 times 10 to the power of minus 23 g, while comparisons of masses measured. Atomic mass. The masses of individual atoms are very, very small. However, using a modern device called a mass spectrometer, it is possible to measure such minuscule masses. An atom of oxygen-16, for example, has a mass of 2.66 times 10 minus 23 g, while comparisons of masses measured in grams would have some usefulness. It is far more practical to have a system that will allow us to more easily compare relative atomic masses. Scientists decided on using the carbon-12 nuclide as the reference standard by which all other masses would be compared. By definition, one atom of carbon-12 is assigned a mass of exactly 12 atomic mass units. AMU. An atomic mass unit is defined as a mass equal to 1/12 the mass of an atom of carbon-12. The mass of any isotope of any element is expressed in relation to the carbon-12 standard. For example, one atom of helium-4 has a mass of 4.0026 atomic mass units. An atom of sulfur-32 has a mass of 31.972 atomic mass units. The carbon-12 atom has 6 protons and 6 neutrons in its nucleus for a mass number of 12. Since the nucleus accounts for nearly all of the mass of the atom, a single proton or single neutron has a mass of approximately 1 atomic mass unit. However, as seen by the helium and sulfur examples, the masses of individual atoms are not quite whole numbers. This is because an atom's mass is affected very slightly by the interactions of the various particles within the nucleus, and also includes the small mass added by each electron. As stated in the section on isotopes, most elements occur naturally as a mixture of two or more isotopes. Listed below, table below, are the naturally occurring isotopes of several elements, along with the percent natural abundance of each. Element hydrogen, isotope 1H, percent natural abundance, 99.985%. Atomic mass, 1.0078 atomic mass units. Isotope 2H, percent natural abundance, 0.015%. Atomic mass, 2.0141 atomic mass units. Isotope 3H, percent natural abundance, negligible. Atomic mass, 3.0160 atomic mass units. Average atomic mass of hydrogen, 1.0079 atomic mass units. Element carbon. Isotope, percent natural abundance, 98.89%. Atomic mass, 12.000 atomic mass units. Isotope 13C, percent natural abundance, 1.11%. Atomic mass, 13.003 atomic mass units. Isotope 14C, percent natural abundance, trace. Atomic mass, 14.003 atomic mass units. Average atomic mass of carbon, 12.011 atomic mass units. Element oxygen. Isotope 16O, percent natural abundance, 99.759%. Atomic mass, 15.995 atomic mass units. Isotope 17O, percent natural abundance, 0.037%. Atomic mass, 16.995 atomic mass units. Isotope 18O, percent natural abundance, 0.204%. Atomic mass, 17.999 atomic mass units. Average atomic mass of oxygen, 15.999 atomic mass units. Element chlorine. Isotope 3Cl, percent natural abundance, 75.77%. Atomic mass, 34.969 atomic mass units. Isotope 3Cl, percent natural abundance, 24.23%. Atomic mass, 36.966 atomic mass units. Average atomic mass of chlorine, 35.453 atomic mass units. Element copper. Isotope 3Cu, percent natural abundance, 69.17%. Atomic mass, 62.930 atomic mass units. Isotope Cu, percent natural abundance, 30.83%. Atomic mass, 64.928 atomic mass units. Average atomic mass of copper, 63.546 atomic mass units. For some elements, one particular isotope is much more abundant than any other isotopes. For example, naturally occurring hydrogen is nearly all hydrogen-1, and naturally occurring oxygen is nearly all oxygen-16. For many other elements, however, more than one isotope may exist in substantial quantities. Chlorine, atomic number 17, is a yellowish-green toxic gas. About 3/4 of all chlorine atoms have 18 neutrons, giving those atoms a mass number of 35. About 1/4 of all chlorine atoms have 20 neutrons, giving those atoms a mass number of 37. Were you to simply calculate the arithmetic average of the precise atomic masses, you would get approximately 36. 34, 969 plus 36, 966, slash 2 equals sign 35, 968 atomic mass units. As you can see, the average atomic mass given in the last column of the table above, is significantly lower. Why? The reason is that we need to take into account the natural abundance percentages of each isotope in order to calculate what is called the weighted average. The atomic mass of an element is the weighted average of the atomic masses of the naturally occurring isotopes of that element. The sample problem below demonstrates how to calculate the atomic mass of chlorine. Sample problem 4.3, calculating atomic mass. Use the atomic masses of each of the two isotopes of chlorine, along with their percent abundances, to calculate the average atomic mass of chlorine. Step 1, list the known and unknown quantities and plan the problem. Known, chlorine 35. Atomic mass equals sign 34.969, atomic mass units and percent abundance equals sign 75.77%. Chlorine 37. Atomic mass equals sign 36.966, atomic mass units and percent abundance equals sign 24.23%. Unknown, average atomic mass of chlorine. Change each percent abundance into decimal form by dividing by 100. Multiply this value by the atomic mass of that isotope. Add together the results for each isotope to get the average atomic mass. Step 2. Calculate. Chlorine 35, chlorine 37, average atomic mass 0. 7,577 times 34. 969 equals sign 26. 50 AMU 0. 2,423 times 36. 966 equals sign 8. 957 AMU 2650 plus 8. 957 equals sign 35. 45 atomic mass units. Note, applying significant figure rules results in the 35.45 atomic mass units result without excessive rounding error. In one step. 0. 7,577 times 34. 969 plus 0. 2,423 times 36. 966 equals sign 35. 45 atomic mass units. Step 3. Think about your result. The calculated average atomic mass is closer to 35 than to 37 because a greater percentage of naturally occurring chlorine atoms have a mass number of 35. It agrees with the value listed in the table above. Practice problem. The element bromine consists of two naturally occurring isotopes. The isotope with a mass of 78.92 atomic mass units has a percent abundance of 50.69%, while the isotope with a mass of 80.92 atomic mass units has a percent abundance of 49.31%. Calculate the average atomic mass of bromine. The atomic masses for each element on the periodic table are average atomic masses. For later calculations involving atomic mass, we will use these values and round each one to 4 significant figures. Lesson summary. The atomic number of an element is equal to the number of protons in its nucleus. The mass number of an element is equal to the sum of the protons and the neutrons in its nucleus. Isotopes are atoms of the same element that have a different mass number because of a variation in the number of neutrons. The average atomic mass of an element can be calculated from the atomic masses and percent natural abundances of each naturally occurring isotope. Reviewing concepts. 1. Why are all atoms electrically neutral? 2. How many protons are in the nucleus of each of the following atoms? 1. Neon. 2. Gold. 3. Strontium. 4. Uranium. 3. What part of Dalton's atomic theory is disproved by the existence of isotopes? 4. Which isotope is used as the reference standard for the atomic mass unit? 5. The average atomic mass of all naturally occurring lithium atoms is 6.941 atomic mass units. The two isotopes of lithium are lithium-6 and lithium-7. Are these isotopes equally common? If not, which is more plentiful in nature, and how do you know? Problems. 6. A certain atom contains 28 protons, 28 electrons, and 31 neutrons. Provide the following. 1. Atomic number. 2. Mass number. 3. Name of element. 7. How many protons, neutrons, and electrons are in an atom of cesium-133? 8. Complete table below. Question 8. Complete the following table. Table for problem 8. Row 1. Isotope, sodium-23. Nuclide symbol, blank atomic number, blank. Mass number, blank. Row 2. Isotope, 7533 as. Nuclide symbol, blank atomic number, blank. Mass number, blank. Row 3. Isotope, silver-108. Nuclide symbol, blank atomic number, blank. Mass number, blank. Question 9. Which of the following is an isotope of 4018R? Explain. A 4020 Ca B3918RC 4018R. Question 10. Fill in the following table. Table for problem 10. Row 1. Isotope, hydrogen 1. Number of protons, blank. Number of electrons, blank. Number of neutrons, blank. Nuclide symbol, blank. Row 2. Isotope, hydrogen 2. Number of protons, blank. Number of electrons, blank. Number of neutrons, blank. Nuclide symbol, blank. Row 3. Isotope, beryllium 9. Number of protons, blank. Number of electrons, blank. Number of neutrons, blank. Nuclide symbol, blank. Row 4. Isotope, aluminum 27. Number of protons, blank. Number of electrons, blank. Number of neutrons, blank. Nuclide symbol, blank. Question 11. Fill in the following table. Table for problem 11. Row 1. Element, nitrogen. Symbol, blank. Atomic number, 14. Mass number, blank. Number of protons, blank. Number of electrons, blank. Number of neutrons, blank. Nuclide symbol, blank. Row 2. Element, blank. Symbol B. Atomic number, 11. Mass number, blank. Number of protons, blank. Number of electrons, blank. Number of neutrons, blank. Nuclide symbol, blank. Row 3. Element, blank. Symbol, blank. Atomic number, 30. Mass number, blank. Number of protons, blank. Number of electrons, blank. Number of neutrons, 35. Nuclide symbol, blank. Row 4, element, blank. Symbol, blank. Atomic number, blank. Mass number, blank. Number of protons, blank. Number of electrons, blank. Number of neutrons, 77. Nuclide symbol, 116. Row 5, element, blank. Symbol, Phi. Atomic number, 26. Mass number, blank. Number of protons, blank. Number of electrons, blank. Number of neutrons, 56. Nuclide symbol, blank. 12. The element tungsten, W, is known best as a metal that is used as filaments for light bulbs. Naturally occurring tungsten consists of the 5 isotopes shown below. Calculate the atomic mass of tungsten, isotope atomic mass percent abundance, tungsten 180 100, and 79.947 atomic mass, units 0.12%. Tungsten 182 100, and 81.948 atomic mass, units 26.50%. Tungsten 183 100, and 82.950 atomic mass, units 14.31%. Tungsten 184 100, and 83.951 atomic mass, units 30.64%. Tungsten 186 100, and 85.954 atomic mass, units 28.43%.